Now we'll consider the subgroups and eventually rings and subrings leading up to the idea of a field. Let's consider a group G, and a subset of G, which we'll call H, such that 1 is an H and A times B is an H whenever A and B are an H. Additionally, we have that the inverse element of any element A is also an H. Therefore, we see that H also has the structure of a group with the group's operation, with namely the group operation of G as the operation for H. Such a subset is called a subgroup of G. And on the subgroup, we can define the mapping phi from G to H is called this is a homomorphism of groups if and only if it is the case that phi of A times B is equal to phi of A times phi of B for all elements A and B in G. We will note an important thing to note is that the idea of a group, that the idea of a homomorphism is not defined only for subgroups. In our definition, we will note that the mapping from G to H is between two groups and not from a group to its subgroup, or any of its subgroups. A group homomorphism preserves some other aspects of the group automatically. Namely, if we denote the identity element of the set G as 1 sub G, and the identity element of the group H as 1 sub H, then, since we have that phi of 1G is equal to phi of 1G times 1G is equal to phi of 1G times phi of 1G, then we apply cancellation on H, and we see that phi of 1G is equal to 1H. And since we have that the homomorphism respects multiplication, then we have phi of A is equal times phi of A inverse is equal to phi of A times A inverse is equal to phi of 1 times G is equal to 1H. So we have phi of A inverse is equal to the inverse of phi of A. A group homomorphism that is also a bijective mapping is called a group isomorphism because it preserves all of the structure of the group and they have the same size in a sense. Namely, there's a bijection between them. The inverse mapping of a group isomorphism is also a group isomorphism, which will denote phi inverse, which goes from H to G. And we can identify these groups by through this isomorphism. As an example, we see you can see that any group of order 4 must be isomorphic either to Klein-Zwer group or to the cyclic group of order 4. So therefore, up to isomorphism, there are exactly 2 groups of order 4, both of which happen to be abelian. The smallest non-abelian group is one of order 6, which we'll see in the future. Additionally, it might be a good exercise to verify that any 2 groups of order 4 must fall into must be either isomorphic to Klein-Zwer group or the cyclic group of order 4. So far, we've just been discussing groups which have a single algebraic operation, but many sets we're familiar with have 2 separate algebraic operations, so let's consider them. These are called rings. The basic structure of interest is the ring, and it's defined as a set R with 2 distinct specified elements, namely 0 and 1, which elements of R, and we have the operations sum and product on any 2 distinct elements of R, such that A plus B is in R and A times B is in R. And additionally, we have that the set R must obey the fact that R is an abelian group under the sum operation with the identity of 0. Namely, that if we consider R just under the sum operation, then it must be an abelian group with its own identity element 0. That's why we defined that there are distinct elements 0 and 1. These will come to discuss what we'll note that 1 is the identity operation with respect to the operation of multiplication. And that's the second point, that the product operation is associative and commutative, has identity element 1 in R, and so A times B times C is equal to A times B times C, and A times B is equal to B times A, and 1 times A is equal to A times 1 for any elements A, B, C, and R. And finally, we have that the operations are distributive in the sense that A times B plus C is equal to A times B plus A times C for any elements A, B, C, and R. Some books may define the idea of a ring differently. Some may define abelian rings, monoid rings, a lot other objects. So for now, just note that this is the definition we're using for rings. Since we have a group, we will note that we have inverses for any element with respect to addition. So we say the additive inverse of an element A is denoted as minus A, and we call that the operation A plus B is called addition, and A times B is multiplication, as might be suggested by the notation. However, the additive identity 0 plays a special role in multiplication. Because we have the fact that we have distributive law, that means that A times 0 is equal to 0 for any A, and since A equals A times 1, then A times 1 plus 0 is equal to A times 1 plus A times 0, is equal to A plus A times 0. So by cancellation, we have A times 0 is equal to 0. Namely, that for any ring, the additive identity element times any element will give you back the additive identity element. Another consequence in a similar fashion is that minus A times B is equal to minus A times B. Since we have that A times B plus minus A times B, we reverse the distribution. We get A plus minus A times B equals to 0 times B is equal to 0. So we also have we have a result. And additionally, we have that negative A times negative B is equal to A times B in a very similar way. It may be worth it to, if you don't see it immediately, to try and reprove in the same way we just did that minus A times minus B is equal to A times B. And in particular, this generalizes, and we have minus 1 times minus 1 is equal to 1, where negative 1 is the inverse of the multiplicative identity element 1. That's where we'll stop for today. Thank you.